Hello class, welcome to the final segment in Lab 3. And in this final segment, we will take a look at how to evaluate derivatives on a discrete grid space, which will then allow you to calculate temperature gradients at every point along a grid, which is something that you'll need to be able to do to complete the programming project that you've been assigned. So when we're working with most of your experience with derivatives is probably with calculating derivatives of nice continuous functions. So you give a function you just be given a function, you calculate the derivatives, that's your final answer, and then everyone's happy. That is, if you get the correct derivatives, then everyone's happy. That works pretty well, and you can calculate a lot of useful things doing that. But here comes the question: how do you calculate? What if you're not given a function? Let's say you're given a whole grid of numbers, and you have to calculate, say, the derivative in the x direction and the derivative of the y direction. There are several techniques that can be used to estimate those derivatives. You can't calculate exactly, but you can get pretty close to the actual number. There are several techniques that you can do that, just so you know that there is more than one. But the main technique that I'm going to show you is the simplest one and the one that I'll expect you to use to complete the programming project. So with that, let's go ahead and dive right into it. So just a quick review of how a derivative is defined. So in this case, a partial derivative of some function t with respect to x, you take your increment as you go to 0 of t of x plus delta x, y comma z minus t comma x comma y comma z, all that divided by delta x, and you let the limit of delta x go to 0. Now there are actually multiple ways that you can redefine this derivative. One is, instead of doing x plus delta x, you can do x minus delta x, but then you also end up with this negative sign in the denominator. That's just an alternative way of calculating the same thing. And it also turns out that another way of doing this is tx plus delta x minus tx minus delta x, and all that divided by 2 delta x, and it's the same limit as delta x goes to 0. And as we'll see later on, this form of the derivative is highly desirable when you're going to calculate stuff on discrete grids, and we'll see examples of that later on. But the main thing I want to focus on is getting the mathematical definition out of the way. This is going to be the main thing that we're going to be focusing on. And if we want to do that in the y direction, we're going to do the same process. So in this case, we let delta y go to 0. We hold x and z constant and let y change. And again, we can do the same definition. So y minus delta y over minus delta y, again, letting delta y go to 0. And then same thing over here, or similar idea over here. And if we want to, we can approximate that. So instead of letting this limit go to 0, we can just take the limit out of the equation, and this basically gets into the idea of approximating what the derivative would actually be. So if we want to approximate what dt dx is, then we just simply remove the limit. We just pick as small of an increment in the x direction as we can, calculate this numerator, and divide by that same small increment. And again, we can do that for the other forms of the derivative. So we can do that for x minus delta x over minus delta x, and then we can do it for x plus delta x minus delta x, all divided by 2 delta x. And again, when working with discrete data, this form is usually the most accurate form. And again, we can do the same thing for dt dy. Again, remove the limit from the equation, and we can approximate that using any of the forms that we have here. So let's go ahead and, so again, we want to focus on these particular forms here because is in practice, this is something that's not really, there's no real mathematical basis for this. It's just in practice, these forms, these particular approximations typically give us the most accurate and reliable results. So those are going to be the ones that we focus on when we're going to calculate or estimate what the temperature gradient is at each point along a grid. So let's actually take a look at an example of how we can apply this idea. So this is the same grid that's in the file that's been posted on Canvas. So if you want to reference, so that again, that's the file that contains all the Python code. It's the exact same grid. So let's consider a grid point that occurs. Let's consider this grid point right here, the one that's highlighted in blue. So this would be, if we're working in the convention of computers, this would be entry 0, or this would be row 0, column 0, row 0, column 1, row 0, column 2, row 1, column 2, row 2, column 2. So that's where these numbers come from, just using the standard convention of computers. And let's say that each individual value that appears in this grid, the grid spacing is 10 kilometers in the x direction, or the width is 10 kilometers, and the height is 10 kilometers as well. So that means as I jump from this grid to this grid, as in going from this grid point to this grid point, I'm going a distance of 10 kilometers. So if I'm going from the square with the 20 to the square with the 23, I travel a distance of 10 kilometers. And if I go from this 20 to this 21, I'm also going a distance of 10 kilometers because the grid spacing in the vertical direction is also 10 kilometers. So if I go from this grid point to this grid point, that's 10 kilometers. Then this grid point to this grid point, that's another 10 kilometers. So from going from this grid to this grid point, I've traveled a distance of 20 kilometers. And if I go from this grid point to this grid point, that's now 10 kilometers in the y direction. And if I go down to the next grid point, that is now 20 kilometers in the y direction. So to get to this grid that's highlighted in blue, I have to go 20 kilometers in the x direction, 20 kilometers in the y direction. And you can generalize that by using an equation like the following. So if you want to get your actual x coordinate, then you would just take the grid spacing in the x direction and multiply that by the grid number that you're interested in. So again, at 0, this top left one, at x equals 0, then xi is also 0. So that would just be 10 times 0, which is 0. And then here, xi would be 1. So that would be 1 times your grid spacing in the x direction, which is 10. So that would give you a distance of 10 kilometers in the x direction. And the same thing for the y, except here you use the grid space or the grid height in the y direction, but it's the same idea, just on a different axis. All right, so hopefully that sort of makes sense how all that works. So here if I consider this to be the origin, then I am 20 kilometers in the x direction from the origin and 20 kilometers from the y direction from the origin. Now let's try and estimate what the temperature gradient is here. Because you can see how if we go in the west and east direction here, the temperature does vary, and then it also varies as we go in the north-south direction. So clearly there's some sort of temperature gradient there, and now we're going to go about the process of trying to estimate what that temperature gradient is. So again, using the form of the equation here that's most reliable or most accurate, the one that we prefer to use. So if we plug in our values here, so our actual x value here is 20 kilometers. So 20 kilometers plus our grid spacing, which is 10 kilometers. So that would be the temperature at x equals 30 kilometers, which would be this 56 here, minus our temperature at 20 minus delta x. Again, delta x is 10, so 20 minus 10, that's 10 kilometers. So that would be the x value at x equals 10 kilometers. So, and again, we're holding y constant. That's the whole idea behind a partial derivative with respect to x. We hold all the other variables constant. So we're still at y equals 20 here. But here we have, so here we're taking 20, so here we're taking the temperature at 30 kilometers, subtracting it from the temperature at 10 kilometers, and then dividing that by 2 times the grid spacing. So this would give us 56 degrees Fahrenheit, if this is in Fahrenheit, minus 25 degrees Fahrenheit. Again, this is the temperature at x equals 30 kilometers, the temperature at x equals 10 kilometers. Divide that by 2 delta x, we get 56 degrees Fahrenheit minus 25 degrees Fahrenheit, divided by 2 times 10 kilometers. And if you do that calculation, you'll get the temperature gradient at that point is, in the x direction, is 1.55 degrees Fahrenheit per kilometer. So that takes care of the x direction. And one other thing I should probably point out is this xi and this yi, if you're working with a list or an array, these would be the actual numbers that you plug into the brackets to get a particular entry out of the array. And we'll take a look at how this actually translates to Python code a little bit later on. But let's also take a look at how we actually calculate the meridional component, or the temperature gradient in the y direction. So again, we use this form, just using this form of the derivative. So this time we're holding x constant, so we're staying in this column. And again, this blue box, this is at y equals 20 kilometers, so we want the value at y plus 20 kilometers, which, as you remember, as the computer is kind of funny, because actually as you go down in the y direction, you're actually going towards, as you go down the rows, you're actually going towards higher values of y. So this 20 plus 10 kilometers will actually give you this entry. This would give you 37 degrees Fahrenheit. And then 20 minus 10 kilometers would put you in this grid point. So this would give you 37 for this term. T at 20 plus delta y, that would be 37 degrees Fahrenheit. And then as you go in the y direction, as you go in the negative y direction, what the computer would consider the negative y direction, that would be 20 minus 10 kilometers, which would give you this grid point. So this would give you 37 minus 35 degrees Fahrenheit. And again, divide that entire thing by the grid spacing in the vertical direction, or I should say in the y direction. And if you actually calculate that out, you'll get that dt dy is equal to 37 degrees Fahrenheit minus 35 degrees Fahrenheit divided by 2 times 10 kilometers, which will give you 0.1 degrees Fahrenheit per kilometer. So that's the mathematics behind this. Let's see how this actually translates to Python code. So if our temperatures are stored inside of a list, it's the main thing that we're going to focus on right now. So again, we're looking at the same entry here. So if we're interested in some point x and y, and if you want to, in the Python file that you've been supplied, you can go ahead and play around with the values of x and y here. So you can see what the temperature gradient is at different locations, and you can see how the program can calculate the temperature gradient at any given value of x and y. Well, not quite any value of x and y, as you'll see in the file. This calculation doesn't work very well, say if you're at this grid point at x equals 0, y equals 0, because there's no data to reference over here. So we have to use a different form of the derivative, but I'm not going to make you worry about the edges. So I'm not going to make you worry about these grid points that I'm moving the cursor around for the project. I only want you to worry about the interior points, the ones that are not next to the edge. Next to the edges, I should say. But to see how this actually translates to Python code, so this x right here, this variable x right here corresponds to this, and this variable y right here corresponds to this. And what I want to do to calculate the x derivative is I want to hold y constant, because the first entry is the row, the first entry, or the first set of brackets is the row, just remember that, and the row corresponds to the y value. So to calculate the derivative in the x direction, I need to hold y constant, and I need to vary x. So to hold y constant in this nomenclature that we have here, we need to hold the row constant, we need to stay on the same row, and then vary the column that we're sampling. So we want the next column over. So if this is column number 2, we want column number 3, which is what this gives us. And for the first term, and for this next term, we want the next column over to the left. So if this is at x equals 2, if this is the second entry in our grid, then we want entry number 1, or column number 1. So in this case, I'm getting column number 3. Here I want column number 1. And I pull those two entries out of our list, out of our two-dimensional list, do the math on top, and divide by 2 times our grid spacing, which should give you the exact same result that we had on the previous slide, which is 1.55 degrees Fahrenheit per kilometer. And then finally, to calculate the temperature gradient in the y direction, and since the y direction corresponds to the rows, we're going to vary the row but hold the column constant, because remember the column corresponds to the x value. So by doing this, we're going to vary the y, so we want this value minus this value. So y plus 1 minus this value. And this is also where things can get kind of confusing, because you also have to keep in mind how the computer reads things. So you see the gradient vector itself would point from, along the y-axis would point from north to south, which normally would be in the negative direction, but in the computer's case, that would actually be in the positive direction. So just something to keep in mind. Be very mindful of the signs there. Just keep that computer convention in mind. I know computers can be weird, especially in this case, but just keep that in mind as you're evaluating these things. So we want the next row down minus the row up. So we want the entry at row number, so if y is equal to 2, we want the next row down, which would be row number 3, minus the value at row number 1, again holding the column constant, which is what this corresponds to. So this would be the next row down, this would be the next row up. Do that math, divide by the grid spacing, and then get a result. And if you do this for an array, it's very similar. It's the same order, row and column, except here instead of using 2 sets of brackets, you just have 1 set of brackets, and then the row number and the column number are separated by commas. But it's the same exact idea here. So hopefully that sort of makes sense how all that works. You might need to, to better understand this, you might need to watch this again multiple times and play around with the Python program that's been supplied on Canvas. But hopefully this sort of makes sense how this works. But that in a nutshell is basically how you can, I wouldn't necessarily say calculate, but how you can estimate the temperature gradient on a discrete grid as opposed to working with a continuous function. So that's going to do it for this final segment of Lab 3. And of course, that means it's going to do it for Lab 3. So with that, I wish you the best of luck on the programming project. And of course, if you have any questions, you have my email address. So with that, that concludes Lab 3.